Good afternoon, ladies and gentlemen. I see that a lot of participants are joining our webinar, so we wait a few minutes, 1 minute, see where we go. Okay, then I propose that we will start. Thank you very much for joining second session of our webinar series about large thermal heat storage. Today, the focus will be on high temperature BTES, closed loop systems. Thank you very much for joining. The webinar series will be hosted by me, Bas Gottschalk. I'm business developer of IF Technology on geothermal systems. And the webinars are supported by the RVO, Dutch Institute to Stimulate Business in the Netherlands and abroad, and also TKI Urban Energy. The program is related to the IEA and the technology collaboration program from the International Energy Agency, focused on energy storage. And we have worked within Task 39 on large thermal energy storage systems for district heating systems. Just a few guidelines for this webinar. We have disabled all the cameras and mics because there are many participants. If you have any questions, then please use the Q&A box. Then during the session, we will try to answer already some of your questions. And please be aware that the chat function is not working, and also raising your hands digitally will not work for this session. All the webinars will be recorded, and including the presentations will become available afterwards. We're also working on the fact sheets of the 4 technologies, so they will be ready also after the sessions. Why are we working on this? Because we are in the middle of the heat transition, as you know, and there are many sources like cheap geothermal, solar, industrial heat. But the challenge is that during summertime, we don't need so much heat, but in wintertime, we need a lot. But most of the systems can produce a lot of heat during summertime. So the idea is that you can store the surplus in summertime and reuse it during wintertime when we need extra heat. And that's why we have a couple of technologies like tank storage, pit storage, borehole storage, or thermal energy storage. Now, the last one has been dealt last week, and today we will look for the closed loop systems. Now, the task has been described in objectives and subtasks. You can read them afterwards, and if you are interested in a more detailed program, then please listen to our previous webinar, because Wim van Helden has explained in more detail what exactly Task 39. This is an overview of all the partners. Most of them are European, but also the US and Canada are partners in the program. For today, the agenda is that first Adip Galantar will present, and then we give the floor to Julian. Between the sessions, we have a short Q&A session, so please drop your questions in the Q&A box, and then we can take care for that. Based on many requests from the previous webinar, we have launched a Dutch symposium for HTO, high temperature ATO system, on the 28th of March next year. If you want to get informed about the program, then please leave a message on the website iftechnology.nl. It's nearly finished, so I hope it will be today, else tomorrow, or else next week. So I think it will be good to give the floor to Adip Kalantar. He is currently head of R&D in Mufiotech Group, a geothermal organization established in 2002. Adip earned a PhD in polymer technology from the university in Sweden, and he has expertise in geothermal applications and is also involved in writing standards and codes for various organizations and giving lectures in some universities. Adip is member of the Swedish Institute for Standards and the International Ground Source Heat Pump Association, and has served on the European Committee for Standardization of constructions of backfilled and grouted borehole heat exchangers. He's also a member of the expert group in task 38 and 39 for the energy storage technology collaboration. And today, Adip, you will have the floor to give us an overview of the high temperature borehole thermal energy storage systems.
Hello, everyone, and thank you, Bas, for a very nice presentation and introduction of the overview of the whole product. I'm very happy to be here and to give you an overview of the borehole thermal energy storage, and also I try to my best to give you some more information about that one. Shall I share my screen right now, Bas?
Yes, please, please.
Do you see right now?
Yeah, and then in presenter mode.
That's correct.
Yes, it's fine.
Okay. Yes. As you can see, the topic that I'm going to present today is the high temperature borehole thermal energy storage. And for today, first of all, I would like to use this opportunity to introduce a little bit about the Movitech and our background and what we are doing and what type of the technology we are using right now. And then I will go with the heater storage technologies. Already Bas has explained it, that we are focusing on this task 39. And then I will a little bit more focus on the borehole characteristics, the parameters can affect on the BTES. And I will review also one case study, and then go to the some challenges that we are facing with the very high temperature of the BTES and future work that we are working on it. And then I will wrap up my discussion. Movitech is one of the European manufacturer of the shallow geothermal product. We have our own factory in different European countries. The headquarter and one factory is located in Sweden, but also we have other factories in Finland, in also Netherlands, Krakow in Poland, also in Norway and UK. In this picture, I think very generally you can see the old product that we are producing. As you can see in this picture, there are many boreholes that has been drilled into the ground. Perhaps it's not possible to see the boreholes, but you can see the pipes that comes out from the boreholes. And then if we have more than one boreholes, then the pipes should be connected to each other. So we have some kind of the manifold and manifold chamber in order to take care of the connections between each boreholes. And then finally, we have two main big pipes that goes to the heat pump and comes back from the heat pump. This is the more or less the very schematic picture of the borehole as a borehole thermal energy usage in a different application. It can be for the heat storage, or it can be as a heat source or heat sink. But today we will focus on the heat storage. If we look at the borehole heat exchanger development, usually or in a very big group, we have two different ways. Either we should go very deep borehole, or we have a little bit different temperature. For the different length of the borehole, up to 450-meter closed loop system, already we have solutions and are commercialized and are in the use in many countries. And then we have some development between 400 and up to 650 meters that right now we are working. And then also the next step would be a little bit more deeper boreholes between 600 meters up to 1 kilometer, and again above 1 kilometer up to 2,000. That most probably wouldn't be any closed system, and it would be more open system. When it comes to the temperature applications, up to 40 degrees Celsius, already we have the solutions and are commercialized. From the 40 to 70, we have done some prototype and demonstrations that today I will share with you some of the results from that one. But above 40, up to limited of the 100 degree, we are doing some research on, and then I will share some information about the progress about that one, but it's not really commercialized yet. I think Boss has already mentioned 4 different technology that we are working in the task 39, PTES, TTES, and also borehole thermal energy storage that I'm going to explain it a little bit more in this presentation. And I will try also to give you a little bit overview of the comparison and where we can use the BTES, but at the same time, most probably the other technology cannot be used. And in that case, or in that perspective, the BTES can be used as a complementary. It's not going to compete with this technology. Definitely, any of them has their own characteristics and their own situation that might be work in some specific area, but the other technology might not work in other areas. The key factors for the borehole, if we look at just the one borehole, usually we have the collector or borehole heat exchanger inside of the borehole, and many parameters can affect of the performance of the collector. And usually we are looking, or the only thing that we can manage or engineering in the borehole thermal technology, reducing the borehole thermal resistance. And the parameters can affect on the performance of the borehole thermal energy storage. I listed here, for instance, the borehole radius or the depth of the borehole. As I mentioned earlier, we are right now looking for deeper and deeper borehole. But when it comes to the borehole thermal energy storage, it might be slightly different. We might need a little bit more shallow in order to reduce the heat loss from the bedrock. The flow rate is one of the process parameters that can be controlled and optimized. The thermal interaction between the upward and downward, usually if we have a very deep borehole, it might be some thermal interaction between the upward and downward, and usually we try to avoid of this thermal interaction. And of course, the space between the each leg between the upward and downward, and of course, thermal conductivity of the backfilling material, and many other hydronic parameters that should be considered when we design of the B-test. But if we look at the storage itself, a little bit bigger picture of the combinations of the different boreholes, then the size of the storage and also the shape. In many cases, we have the cylindrical shape of the borehole thermal energy storage, and also the configurations, how the boreholes are connected to each other. Usually, in many cases, from the center of the storage up to the corner of the storage, we will have some kind of the series of the connections, and then from the end of the storage, we will have some parallel into the technical room and the other connections. And of course, number of the boreholes and depth, and the highest and the lowest temperature of the fluid can be very important parameters. In some countries, perhaps you know that in Scandinavian, we don't use any grouting and backfilling material, but in some other countries, based on the rules and regulations, are mandatory. So this natural convection of the groundwater inside of the borehole also might be a big influence in the performance of the borehole thermal energy storage. And of course, we have a lot of mechanical stress and hydronic parameters that should be considered, and then a lifetime of the system and techno-economical analysis of the whole concept. One of the important parameters that is not related to my job, at least for this today, is the geology and ground property. Usually for the normal application of the borehole, we are appreciated of the groundwater flow, but for the thermal energy storage, we prefer not to have some kind of the ground flow water in order to not to lose thermal energy storage. And here again, you can see the effect of the different conductivity of the or thermophysical properties of the material that we are using inside of the borehole as a collector. Here you can see that the different polymers that are most of the cases are used for this type of the application based on their thermal conductivity and the relation between the thermal conductivity and the collector resistance. And also the mechanical property, because if we can increase the mechanical property, of course, we can decrease the wall thickness of the material, and then reduce the resistance inside of the borehole heat exchanger. We managed one case study in Norway. There is one school in Drammen. Here you can see the location of the city of the Drammen is very close to the Oslo. And in this picture, you can see the overview of the school. In the 2018 and 19, the project has been started, and it was decided to use some waste heat or some heat during the summertime, as Bas has mentioned, that during the summertime we have a lot of waste that can be stored in different way, and we can reuse it during the winter time. We use this concept also for this project. As you can see in the top of the roof of the school, we use the PV panel and also in some part PVT panel. And during the summertime, this solar panel produce the electricity in order to run the heat pump. And during the summertime, with the heat pump, we store the heat into the to the boreholes. The boreholes area is the 100 boreholes with the depth of the 50 meters, and each boreholes are distance from each other around 4 meters. And the temperature is of the borehole 50 to 60 meters. 60 something Celsius. In this picture, you can see the overview of how the boreholes are connected to each other, and then the horizontal pipes that are connected to the technical room. In here, you can see the schematic of the storage is like a cylindrical shape with a 50 meters depth. And then we had some boreholes or for monitoring of the results. Here you can see the results of the storage for the first and second year. We just reject the heat to the boreholes, and during the 2020 and this year we used as a borehole storage and charge and discharge. The important thing that here you can see, if we compare it this with this one, that both of them has been charged. As you can see, the temperature of the storage has been decreased, and also the storage capacity has been increased. So as you can see, the temperature of the surrounding or the outer layer has been increased slightly during the time. Usually we use the polyethylene as a raw material for the different technology, particularly for the borehole heat exchangers. They are extremely nice material. They are flexible and can be coiled. Many parameters or positive characteristics has made possible to use the polyethylene for different application. Even the pit storage also, they use a lot for the polyethylene. One of the biggest issue with this material is the lack of strength during the very high temperature. As you can see here, the flexural modulus of or mechanical property of the polyethylene has been decreased a lot when we have the higher temperature. Some of the technologies has been introduced into the market in order to make some other type of the polyethylene that is called cross-linked polyethylene. I don't want to go to the details of this cross-linked. We have many different type of the cross-linked polyethylene, and we also recently developed our own cross-linked polyethylene. It's completely new material and new chemicals, and right now we just recently produced 2 collectors that we expect can be used up to 95 degrees Celsius and can be used for the district heat system. These 2 collectors are going to install in the one city in the north part of the Norway, and we are going to do some field tests and also 3 years of the aging test in order to look at the lifetime and the performance of the collector in the very high temperature, like 95 degree. If I want to wrap up my presentation, there are many cases that you can use the waste heat from the industry. In here, you can see we have a lot of different applications that they use the heat for their process. And when the process is finished, they need to get rid of that heat. So we have a lot of spot heat in the city or in the municipality that we can use and as a heat source for the storage. The case study that you have seen, it was the on-site heat. So there's no necessary to be a very big scale of the heat storage. As you can see, this case study was very small, and it was just for the one school that we use the on-site heating in very small scale. And the characteristics of the borehole thermal energy storage is that you can use it in everywhere, almost everywhere you can use it. There is no any limitations for that one. The only thing is that I would like to emphasize that is just one solution. It's not possible to use in all of the application. Definitely, it should be combined with the other technology. And right now, with the current technology, is working perfect with a little bit lower temperature, up to, like as I said, 70 degree, and also some small scale. And whenever we can use as a on-site heat. Definitely, when we use the hotspot heat from the municipality, definitely we can reduce the peak load from the grid, and also a lot of other properties. As Boss already mentioned, that we are a part of this task 39, and I would like to express to thank all of my colleagues and friends from this task 39 that can give us this possibility to share our information between each other. And this is a very nice picture that we recently visited in the BTES storage in the north of Germany. Thank you for listening. Boss?
Yes, thank you very much, Adib. Just try to put my screen on.
Yeah, just let me see if I can stop sharing.
Go to the next one. Okay, thank you very much, Adib, for your very interesting presentation. And yeah, that we have a better idea about also the materials you are using. We have time for a few questions. David, during the last minute, new questions appear up. So can you bring in some questions?
Feel free to stop sharing your screen, Adib. Then we'll see all of us. And I'll also double check.
I think already I stopped sharing or not.
You shared the screen.
Yeah,
I see.
Oh,
good. That's fine. No, that's fine. It's all good. The questions that have come in. Yes. First of all, thank you for the presentation, Adib, and also it's nice how you mentioned how BTES can also really be applied in conjunction with other forms of storage, so part of the same local energy system that you're trying to build. I was also trying to think a little bit from the perspective of a bit more of an outsider who might see, okay, there's something being drilled, and in that way, if you look at it that way, then BTES and ATES sound or look similar, but obviously they're different. But maybe we could maybe we can quickly reflect on the differences or the key differences between BTES and ATES.
Yeah, definitely. HT-BTES, I think BOS is the and IF Technology are expert in that one, but we need some special geology that should be aquifer should be available at least in order to run the HT-BTES. But as I mentioned here, for the borehole thermal energy storage, of course, geology is a very important parameter, but in many cases, it can be neglectable.
All right, Bas, could you, yeah.
Yeah, I think we have to go to the next speaker, David.
All right, yeah.
Yeah.
That's all right.
Because time is running.
Yeah,
and
thank you.
I think we try to answer also the Q&A during the session, so that's fine. And maybe we have some time at the end also to discuss about the remaining questions.
Correct. A lot of questions have popped up and they're already being answered. So if Adib can also help with that in a bit, that'd be great.
Perfect.
Cool.
Then I will announce Julian Formhaus. Julian is a Master in Science in Energy, Science and Engineering, specialization in renewable energies and power plant technologies. And he also finished his PhD on the TU in Darmstadt, where he investigated the integration of district heating grids with underground thermal energy storage. And since 2016, Julian is part of the System Development Department of Vattenfall Wärme in Berlin. And he's working on long-term thermal energy storage strategies for Berlin, development of deep geothermal energy, strategic grid development, and also participant in the TALT 39, where he focused on the modeling of UTIS systems. So, Julian, please take over the screen, and then we are very interested in how you integrate BTES with district heating systems.
Okay, thank you very much, Bas, for the brief introduction. Just a small correction. I only started at Vattenfall last year, so not 2016, so quite fresh.
Okay.
And for our Berlin district heating grid, we are looking into different seasonal storage technologies. Borehole thermal energy storage is not in the center for our larger system, but at my time at the university in TU Darmstadt, I made a lot of research on BTES systems, and the things I'm going to present to you today are based mostly on these publications from the university. Okay, so how are borehole thermal energy storage is typically integrated into a district heating system? Well, we usually have a non-dispatchable heat source that where it's meaningful to store heat on a seasonal basis, ideally at high temperatures up to 90 degrees and with low emission factors. Then borehole thermal energy storage is the ground is a very slow heat conductor, which is nice because we don't lose a lot of heat. But on the other hand, we cannot discharge and charge it very rapidly. So usually for the high peaks in the heat demand, we have a buffer storage, which is connected to the borehole thermal energy storage for the daily storage. Then we have a heat pump usually connected to the storage to discharge it to low temperatures and use a lot of the ground capacity for storage. And then since usually it is not economic to cover 100% with this system of the heat demand, we have an additional heat source to cover peak loads as well. Okay, so storage efficiency is obviously a very interesting topic, and here we see that it changes over the years. In the beginning, we lose a lot of heat to the ground, but later on the ground has heated up already, and then the efficiency rises depending on the design and the size of the storage. But one aspect which is quite important is that the efficiency of the storage alone is not the most important factor at all. Here we see how the efficiency is defined. So we charge here at temperatures, here it's 90 degrees, and get the fluid back out of the storage with a varying temperature. And during winter, we discharge the heat with here 30 degrees and get a little bit higher temperature back. And the storage efficiency is just the ratio of the extracted heat to the stored heat. But the important aspect is that the heat that we get back from the storage is on a much lower temperature level than the one that we charged into it. So if you look at a BHE during charging, we maybe have 80 degrees inside the borehole heat exchanger, and inside the ground it will be then 60 degrees because it's a conductive system. It needs a temperature difference, so heat flows. And then if we want to retrieve it, we have to go into the storage with even lower temperatures, for example, 40 degrees. And then, yeah, we have got back 40-degree heat while we injected 80-degree heat. So this is obviously, yeah, one important aspect that we need to consider during the design phase. So how does the grid temperature affect our overall storage performance and the system performance? For this, we made a small study where we have a little fictional district heating system, which is mostly based on our university district heating grid that we have in Darmstadt, where we have a conventional heat source still. We have a ball thermal energy storage with 62 ball heat exchangers, a heat pump, 2 smaller buffer storage, and solar collectors. And in this study, we chose 4 different heating curves for the supply temperature from 110 degrees at the maximum down to 50 degrees for the low temperature district heating. Otherwise, the system was fixed and simulated over 8 years. And here for the 4 systems, you see the storage efficiency, which was the result. And this is not even that different for these systems. But what is more interesting is that for the low temperature system, less heat was charged into the ground because we have lower temperatures and less heat is flowing into the ground, and consequently the capacity is smaller for this system. And then even more important, the COP of the heat pump, because we have lower grid temperatures, we don't need that high temperature shift of the heat pump, and the COP is much better for these low temperature district heating systems. It's always depending very much on the case, but the general trend is always the same. So as a small example, I'm going to show to you the research project we had at the TU Darmstadt campus, where we constructed a medium deep borehole thermal energy storage. As Adib said, this is currently an interesting topic to look into because we have higher temperatures deeper down and we have less groundwater flow. And here we constructed for a small pilot storage only 3 ball heat exchangers with a depth of 750 meter, where the upper, I don't know, 20 to 50 meter are insulated, so we don't lose a lot of heat to the groundwater and store the heat in the deep ground. Okay, so based on these, on this system, we made a lot of different case studies, which I'm going to present to you briefly now. And if you're interested in these, they are all from publications, so please feel free to contact me and I will be happy to share them with you. So the first one was the question, okay, how do we integrate our borehole thermal energy storage into our university grid? And for this, we made a study where we looked at the time frame until 2050 and divided it into 3 sections, used projections for energy prices and emission factors. And then based on other studies, we assumed that the grid temperature can only be reduced from the current state stepwise. While the oldest buildings are renovated, slowly the grid temperatures can decrease and the return temperatures will decrease. And for the integration, we looked at different strategies for the timing of the construction and the decommissioning of our existing infrastructure, which you see here on the right, and the component size that we want to construct. And the existing system right now is mainly based on combined heat and power plant with some gas boilers, small buffer storage, and high performance computer, which has waste heat at around 30 degrees, which is fed with a heat pump into the return of the grid. So for the study, we investigated the phasing down of the CHP, the integration of the waste heat into the return with a heat pump or without, or into the supply with a heat pump, without a heat pump, and solar thermal collectors of varying sizes, and medium deep borehole thermal energy storage with the design of this demonstration storage consisting either of 0, 19, or 37 borehole heat exchangers. And here, briefly, the result, the emission factor and the levelized cost of heat of the investigated system here for an immediate construction at 2025 of all the components that I showed you and the decommissioning of the existing infrastructure, and the size of the dots is the size of our solar collector field that we want to install. Obviously, the more solar we have with larger fields, we have less emissions, but at some point our large storage is even the seasonal storage too small, and then we don't get any improvement and just an increase of our levelized cost of heat. Here's the emission target, which is an average value down to until 2050. In the end, it has to be, I think, like 10 degrees of 10% of 1919 or something like this. So, and here are the other strategies we looked into. So a more conservative strategy with a low speed and small sizes of the components, a stepwise construction in 2030 of all the components, a progressive, which has a maximum system already in 2030, and a gradual construction, which gradually increases the size of our solar thermal collectors and the seasonal storage. And as you can see, this gradual strategy is the most economic way to reach our emission target that we want to reach. And so the actual numbers are not that important. The message is just that this construction and integration into the system should be adapted to the existing infrastructure. If we lower the temperatures, the storage and the solar collectors will get more efficient, and in the future we expect combined heat and power to get less beneficial in regards to the emission factor and the prices. So we slowly decrease these components once they are decommissioned, depreciated. Okay, so the best way is to adapt your construction in accordance with the existing system. Then another question, which is always quite interesting, is if borehole thermal energy storage is possible in regions with groundwater flow. And for this, we made a small study. This system has, again, some solar collectors, buffer storage, small heat pump, the borehole thermal energy storage, a gas boiler for the peak load, and a small heat load. So this is a quite small system with reasonably low district heating temperatures. And the storage in this case is rather small as well, but it works already. We have 18 borehole heat exchangers with 100-meter depth, and 3 of those are connected in series. So we can charge the storage with the center borehole heat exchangers first, then the cooled down fluid that leaves those enters the outer borehole heat exchangers. So we get a natural stratification where the highest temperature is stored in the center of the storage, and we don't lose that much heat. And for the groundwater flow, we varied the hydraulic conductivity of our ground in this shown range and kept the hydraulic gradient, so the gradient of the groundwater table, fixed. And here is the system which has almost no groundwater flow, so only 3 millimeters per year. And here you can nicely see in the top view of the storage that we have quite high temperatures here in the middle, and it's symmetric. And a couple of meters, like 10 meters away from the storage, we already have quite low temperatures. This is the other extreme case where we have the highest groundwater flow with about 30 meters per year. And here you see that a lot of heat leaves our storage area, and the temperatures are as well much lower. We don't have any red here. So this is obviously not the desired case. And on the overall system performance, the result you can see on the left side always the demand. So in red, the demand, the grid losses, the losses from the buffer storage, and the amount which is charged into our borehole thermal energy storage. On the right side is the supply, where we have solar collectors, the amount which is discharged from the storage again, which is in this case 61% of what we stored into it, electricity consumption of the heat pump that is used for this, and the peak gas boiler. And the higher the groundwater flow gets, you see that the less heat can be discharged again from the storage because it leaves our storage region, but it's still not zero. It's about half of what we put into it. And I would say probably at about 10 meters per year, we have a really significant drop of our performance. Before this, it's rather constant. And in addition to this, as I showed you, the temperature which is still left inside the storage region is lower. So we need more electricity for the heat pump to shift it to the grid temperatures, which decreases the COP of the heat pump, which is shown here. Okay. Then last but not least, I wanted to show you a little application example of a real world system which has already been constructed, I think in 2011 or 12, which is the Brædstrup district heating system in Denmark, which you can see here in the aerial view, where we have solar collector fields here too, both amounting to about 18,000 square meters. Then we have some buffer storages here, heat pumps, gas boilers, electrical boilers, and CHP units. And the borehole thermal energy storage, as you can see, or not can see, is located here in this region, which is quite nice. It's underground and you don't see it. And here are some results from the system. In the first years, the storage efficiency in average within this observation period here was about 75%, and the annual charging about 190 megawatt hours. But the issue with this system was that it was much lower than the design numbers were actually. They were up to 510 megawatt hours. And this is due to the fact that the district heating system was had a much higher heat demand in comparison to the design. So the solar collector fields didn't produce that much excess heat during summer, almost no excess heat, which you can see here, these yellow bars, and I think the gray is the heat demand. So we don't have really any excess during summer in some years, which shows you that less heat can be stored seasonally and consequently less heat extracted, which is probably quite important fact that you always need to carefully design your system. And it is good to have a secured excess heat source for storage during summer. Okay, so now to the key takeaway. So high temperatures BTES system, as we saw, can store very large amounts of heat for reasonable storage costs. Basically, these can be scaled to whatever size you want them to be, as much size as you have. And as we showed, we can go further into the depth as well. In our example, we had 750 meters, but yeah, probably 1,000 meters should be possible as well. But on the other hand, the drilling costs increase significantly with the depth as well. Then very high efficiencies are possible, even above 100% because we have an open system of the storage. yeah, we can even discharge more with a heat pump than we charged into it. Yeah, the integration into the overall system, it's much more important than the actual storage performance in the end. And ideally, we should have a high temperature heat source during summer for storage and a low temperature district heating grid. Significant groundwater flow will reduce our storage efficiency, but does not rule it out completely. But at higher flow velocities, it doesn't make any sense anymore. And then in the end, as you saw at the real world application, the storage performance and usefulness are highly dependent on the overall system integration. We need the availability and the temperature level of the excess heat and the grid temperatures. Okay, then thank you very much. And like Adib already showed you, you cannot see very much for a borehole thermal energy storage, and this is pretty much the only thing which you can take a picture of. Thank you.
Thank you very much, Julian. Also good to see that you are practicing your Dutch.
Google helped a little bit.
For sure. Let me share screen. Okay. Next slide. Yes. Okay, perfect. David, do we have some questions for Julian?
Yeah, we have a few questions for Julian, and maybe Adib would also feel like he'd answer some of these questions. Adib has also been answering in the chat. But there are a lot of questions as well. People are also trying to understand a little bit how it works underground as well, and what the construction looks like. And one of the questions, or what people are wondering, is what kind of liquid is used in these kind of systems, just for people to get a bit of an idea. Is it water, just water?
Since these systems are usually operated at higher temperatures, you can basically just use water. Only if you, due to your design, have the fear that it might get close to zero, then you should use a water glycol mixture.
All right.
That's what I know from my experience.
And is that in the systems? But in the systems that that Vattenfall works with, it's water in your systems.
We at Vattenfall in Berlin, we don't operate any borehole storage. This one was from the university where we used water as storage medium.
Oh, okay. Yeah, clear. All right.
Maybe to add one thing, I knew in Sweden they also sometimes use just alcohol as liquid.
Okay. All right. Didn't know that one. All right, fair enough. And the question, a few people have also been asking kind of questions with regards to sort of space, right? And it's nice how you showed the map of what it with the system in Denmark. And can you apply a BTES system under a building? Can you put a building on top of it? Or can you build anything on top of it? Or would you rather not want that? What does that look like with regards to space?
I cannot give you a definite answer, but probably when we go to these high temperature systems, I would probably rather not, because the structural integrity of our building will be much more important. But in theory, I mean, activated piles are quite common under buildings, so that you have these are like, I would say, low temperature borehole thermal energy storage systems.
Yeah, you're referring to the energy piles, or sometimes that's how we call them sometimes as well here in the Netherlands. All right. And maybe this one's also looking, maybe a bus maybe knows. Are there examples of BTES systems in the Netherlands? So maybe these energy piles is actually a bit of an example, actually. But are there other such systems?
Yeah, there's a very interesting case in Groningen, Bedum. It's in the urban area. So they have houses where they put solar collectors on it. and they are harvesting the heat during summertime. They store it in the center. There's a green field where they have the boreholes, and then they use it in wintertime for heating their homes. And the system has been installed in 1983, so it's already running for 40 years. So that's really amazing. Yeah. And I do not have the picture in my presentation, but it's already running for many years in Groningen.
Interesting. There was also a bit more of a specific question for you, Julian. You referred to non-dispatchable heat sources. What do you mean with that? What's non-dispatchable in your case?
In our case, it's like most renewable heat sources, like sun or wind, which are not available whenever you want them, but many times exactly when you don't need them.
Yeah, clear. All right, thanks. Then just another question which popped up with me, and I believe you did explain it, but maybe you could elaborate it on it one more time. You mentioned efficiencies above 100%, and that's because there's a coupling with the heat pump, or how does that work again?
Yes, this can be done with a heat pump, but depending on the design, it could probably, in theory, be even without a heat pump. It's just our storage is not a closed system. It's open to the ground.
Yeah.
And from the basic design, it's the same as a usual ground couple ball heat exchanger system, where we only extract and never charged into it. So there's pretty much a floating line between those systems, where there's no clear definition where does the storage start and where is it just a ball heat exchanger field with regeneration.
Yeah, great. And
I also ask one question, Julian, about the speed of the storage, because we know that from an HT-BTES point of view, you can quickly store a lot of heat by just abstracting and injecting groundwater. Can you tell us something about the speed of a closed loop system? How quickly can you store large amounts of heat? Or is it a slow mechanism?
Yes, it's slow, as I said. I mean, if you have these buffer storages, which, for example, when you have solar thermal collectors, you usually need them anyway. So if you have like a smaller buffer storage for daily peak shaving, then this already can cover all your heat demand. But if you would just couple the borehole storage to your heat demand, probably it would be a little bit difficult to cover all the peaks completely with the storage.
Yeah.
David, last question.
So it's one of the layers in the energy system is also what you're trying to say there.
Yes.
Maybe last one, bit more general. Now that we asked this one last time as well, could you say something about the potential for power to heat with BTES systems? I don't know if that's done in Denmark or if you know of any cases or.
For example, in this system in Denmark that I showed you in the end, we already saw that the heat demand was higher than the solar production, but still there was some heat stored into the BTES, which was due to the power to heat that they installed at the site.
Yeah.
So it can be combined as well. Again, you would probably want to have a buffer storage as well.
Yeah.
Because you want to quickly use your electricity.
Yeah.
With the power to heat.
Thank you. Point. Thank you.
Thank you, Adip and Julian, for the presentation, and David for bringing up the questions to the table. I just want to close the session by mentioning the next session. Next week, we have the topic BTES, pitch storage, and we have two experts, Morten from Bobach and Jonas Sorensen, experts in Denmark. That will become a very interesting session. On the 14th of December, there we go to the tank storage. And also please be aware that for the Dutch audience, we have a special event on March 28th, which will go and focus on the high temperature HT-BTES systems. So for now, I would like to thank everyone. And if you want to have more information about the IEA program, Energy Storage, TCP, then please reach out to Stan van den Broek of RVO. And I would like to thank you for joining the session, and I hope to see you next week again. Thank you very much. Bye-bye.
Thank you.
Thank you as well. Bye.
Thank you, everybody. Bye.